All right, thanks everybody for coming. I think this is supposed to be a lunchtime talk. There's 2 people eating lunch. I haven't had mine yet, so lost in transmission. Well, it's really exciting to have everybody here. In particular, there's plenty of seats over there. In particular, since we're parallel programs, I'm excited to hear about what you're doing, and I hope to give you a very colloquial overview of sort of the broad physical questions that our program is trying to address, right? So, and the program is called Quantum Optics of Correlated Electrons. So, plenty to unpack here. So let me try and start by asking, what are correlated electrons? Why are we interested in them? How do we think about describing them? What are some of the issues? And then let's see how the second part of our agenda, quantum optics, allows us to interface with complementary efforts in AMO physics to try and find new ways of changing materials, probing them, manipulating phases of matter. Okay? Just somewhere there. So it's, on one hand, a really exciting interface. So there's been a lot of efforts in the realm of condensed matter theory and quantum materials in trying to steer systems out of equilibrium using strong light fields. Of course, a lot of efforts in trying to understand spectroscopies. Quantum optics takes a very different approach at trying to understand the physics of single emitters, but very, very strongly coupled to a light field. And so at that interface between strong light matter coupling and extended systems and materials, there's a lot of interesting new physics to discover. So, but let's start with quantum materials and why they're interesting and why they're hard, right? So generally, as for us condensed matter physicists, everything is already a highly effective idealized action at low energies, but the basic starting point is usually a crystal lattice. These might be some ions in some cubic configuration, right? And I'm going to have a bunch of electrons in this crystal lattice. An electron density that can range anywhere from 0 for free electrons in an insulator to maybe 10 to the 23 per square cubic centimeters in something like a metal that becomes a really good superconductor at low temperatures. Okay, so of course in intro E&M we know that there's many commonplace phases, prominently in metal. Electrons are free, they can conduct charge. There are insulators. There are semiconductors. You've all heard about this, I'm sure, in many settings and also with many engineering applications. So that's really not what this program is about, in particular, since we're going to be interested in correlated electronic phenomena. So with examples such as superconductors, quantum magnets, more exotic condensed matter phenomena such as, say, excitonic insulators. I'll try and motivate some of these a little down the line, or charge order. Or even topological phases. Okay, so of course, nobody, I think, needs to motivate why a superconductor is useful, right? I mean, you're using superconductors whenever you go into a hospital and take an MRI, right? Having practical and higher temperature or switchable superconductors would be of tremendous technological importance, right, for electronics devices, for energy transmission, for, again, medical imaging devices, and so on and so forth. Magnetism underpins a lot of the storage technologies that we use for engineering applications, but also sensing of fields, excitonic insulators, charge order compounds. Some of these systems can have multiferroic properties that are, again, technologically important. Topological phases, of course, extremely interesting and have garnered a lot of scrutiny over the past maybe 2 decades in condensed matter physics, but have also practical applications in the sense that they can, for instance, exhibit electromagnetic properties that are robust in a certain sense to impurities, disorder in a solid, etc. So these are really the phenomena that we're interested in. What these phenomena have in common is that for all of these classes of systems, if I wanted to quantum mechanically understand what that state of matter actually is, and I wanted to write down a wave function, that wave function cannot be written as a product over the number of electrons of single particle wave functions. Okay? And that's really what we mean by correlated electron physics. More broadly, these are phenomena that oftentimes defy mean field descriptions in terms of the effective motion of single electrons and require more sophisticated understandings of how the collective quantum mechanical behavior leads to emergent phenomena from the entanglement of many electrons. Okay, so the ingredients that we need for this are actually very few, but that doesn't make the problem simpler. So in a crystal, you might have an ion potential, assuming that the nuclei remain approximately stationary. You'll have Coulomb interactions between electrons. Okay, so the ion potential you can view as an effective potential that governs the kinetics of single electrons in the solid. The Coulomb interaction, however, now leads to interactions between electrons that cease for single particle descriptions to apply. And you might have lattice vibrations. This is very important, for instance, for the conventional theories of superconductivity. There's other ingredients that you could add, for instance, applied external magnetic fields, gating, etc. But by and large, these are the basic ingredients that make up our designed states of matter. And of course, in principle, there's a great deal of technology for understanding their interplay, but tuning their interplay to get a particular phenomenon that we're interested in, say a superconductor, is hard. Right? Functionally, that's a chemical problem with a little bit of tuning that we can do in a physics lab. So the new ingredient that this workshop really hinges upon, or this program, is to ask, well, what if we add photons as a new tuning knob? What if we couple a material strongly to light? What if we couple it to photons? Can photon lead to new emergent phenomena that we couldn't achieve with ordinary chemical tools? All right, and so then the basic scheme, of course, looks almost the same, right? If I wanted to make a sketch, and let's irradiate this material with photons, right? Some electric field. The problem, of course, is that generally the coupling is small, right? We know that the fine structure constant is going to be 1/137, right? Coupling between electrons and matter at the bare level is going to be very small. What can we do? Two things, right? We could look at using strong fields. That has a long history, and I'm going to say absolutely nothing about this, right? This is the realm of ultra-fast dynamics in solids. People blasting materials with strong optical fields, X-rays, terahertz radiation, and looking at the dynamics of many electrons after a pulse, right? Just sketch this. The other option, which is really at the heart of this workshop, is what happens if we confine photons such that they can spend more time to interact with a material, right? And so, sorry for my repeated sketching of a crystal lattice, right? So basically, the name of the game is now, hey, we have a material. What if we embed it in a structured electromagnetic environment such that I have a confined optical mode? So what I'm drawing at the top and the bottom are mirrors. I'm going to put this in quotation mark because there's many, many possible ways of structuring such an environment, starting from ordinary Fabry-Perot cavities to metamaterials and clever engineering tricks. And there's going to be a standing photon mode, a standing wave, right? A photon mode that now hopefully is confined such that the photon that is inside the cavity will be long-lived before it can escape, and hence has an ability to dramatically change the material, even if the bare coupling is relatively weak, right? And so this brings me to the second point of our title. So what is quantum optics, and how does quantum optics come into this? Well, of course, this is the paradigmatic setup that usually is studied in the physics of quantum optics of individual emitters or atoms. Okay, so how this looks like in a quantum optical setting is very simple, but gives us a great deal of intuition for materials. So let's look at light matter coupling for single emitters. Suppose you look at a paradigmatic quantum optical setup. You have an optical cavity. Okay, so I'm going to draw two confocal mirrors here. You again have a confined optical mode. And now suppose I place a single atom in the center of the cavity. Okay, so that single atom, right? In general, we all know our hydrogenic spectra. You might pick a particular atom in which the transition energy between a dipole allowed transition is tuned into resonance with the cavity mode. So as a cartoon picture for how the quantum mechanical model of such an atom actually looks like, I might think of that atom as an effective two-level system with all other interorbital transitions being drastically detuned from the cavity resonance. Okay, so by standard notation, let's call G the ground state, E an excited state. Think of this as a single electron that gets excited between two orbitals. We can tune, so there's going to be a splitting between these two levels, and we can tune the cavity resonance to be approximately resonant with that transition. Okay, so if this is my cavity mode frequency here, then a photon with that frequency can efficiently drive a dipole active transition in a single atom. Okay, and so I'm going to write, I think this is one of two Hamiltonians I will write down, and then the rest is hopefully all qualitative discussion. But this gives us a great deal of intuition if I want to understand what that light matter coupling Hamiltonian actually looks like. So how does the photon field couple to that dipole active transition? Well, simplest coupling I can write down is a dipole coupling, right? Where I couple the dipole operator of the system, okay, to the electric field. Okay, and so that dipole operator is just charge times displacement of charges. The electric field, on the other hand, we'll have to be a little more careful. Yeah. So E in a cavity, if we're interested in quantum effects of the electromagnetic field, we'll have to quantize the electric field, and we'll impose here a standard assumption that we should take with a grain of salt, and we will hopefully revisit with materials, that we might have a single isolated mode confined in the cavity. Okay, so there's going to be some mode function E of x times bosonic oscillators for the cavity photon. Okay, so A and A dagger are annihilation and creation operators for the single cavity photon modes. All right, so of course there's a great deal of information in E of x, right? This will depend or tell us about the single mode profile, and is really one of the ingredients where a lot of the at least experimental optimization goes into. You know, how do we design our fields in such a way that we achieve particularly strong couplings? But let's not jump ahead of ourselves. Let's just look like how this looks like for a single two-level atom, right? If I only consider the dipole active transition between a single ground state and excited state, okay, I can expand the dipole operator and rewrite this Hamiltonian in terms of two terms. I'm going to parameterize it by a coupling constant G. I can take the atom from its ground state and switch it to its excited state by absorbing a photon. Okay. I can also, right, just expanding out this operator, I can also switch the atom from the ground state to the excited state while emitting a photon. And of course, my Hamiltonian better be Hermitian. Okay? So this constant of proportionality, again, carries a great deal of information, but I'm just going to give you a proportionality. This generally scales as with the inverse square root of the mode volume times a dipole matrix element between the E and G states.
This includes the counter-rotating terms. So here you
have counter-rotating terms.
G is correct. Yeah?
That's right, exactly. Yeah. And so actually what you said is precisely right. So this is what we call a rotating term. Yeah, the terminology comes from whether we are going to be resonant or this process conserves energy, right? If we're resonant with the dipole transition, we'll absorb energy omega from the photon field to generate a dipole excitation, right? The second term, of course, looks highly off-resonant, right? Essentially what we're saying, that second term models an excitation from the ground to the excited state while emitting a photon, right? So, in other words, the difference between the initial and final state is 2 times the photon energy if we're on resonant. And so now, having done that, right, ordinarily we would say, hey, you know, this counter-rotating term really shouldn't matter, right, because it's energetically so disfavored. So we can do what's commonly called a rotating wave approximation to just study the energetically resonant dipole excitation process. How this will look like is actually very, very simple. So suppose I take the combined state of my photon field and matter in the cavity. I might have the emitter in its ground state and no photons. I might have the emitter in its ground state and 1 photon. I'm going to assume that the cavity field is tuned to resonance with the dipole transition. Okay. I can also have the emitter in its excited state, but after emitting a photon, and so on and so forth. So this forms a ladder of states. Sorry for the really simplistic picture, but this gives us a great deal of intuition for what will happen in a material. Okay. So this energy again is the cavity frequency, which we're going to tune to resonance with the dipole transition. Okay. As we're now turning on the light matter coupling, what will happen is that these 2 states hybridize, right? I can start from a ground state in 1 photon. That photon can be absorbed to generate an excited state with 0 photons and vice versa. So what we'll find is that these energies split into 2 branches that are split by the dipolar coupling, G. So this is called the Rabi frequency if we're on resonance. And if talking about generic materials excitations, this is commonly referred to as a lower and upper polariton. Okay? So, and of course that ladder continues, but only assumed that we have the rotating term. Okay? So we can now ask, hey, you know, what happens in 2 limits that are going to be very relevant for what we want to do in solids. And I really apologize for the notation, right? This comes from quantum optics, not from us condensed matter theorists. But this is generally referred to as the strong coupling and the ultra strong coupling regime. And just for completeness, there's in fact a thing called a deep ultra strong coupling. Not discussed. So I didn't make this up, but it's true. What people refer to as strong coupling is generally the regime where G is sufficiently large such that if we add 1 more ingredient that, of course, a real-life system always has, right, that cavity isn't perfect. The photon can decay out of the cavity, right? There's mirrors. The mode confinement is not perfect. So there's going to be a photon loss rate. Okay. If my Rabi or my dipole coupling over the photon loss rate is larger than 1. Okay. So what does strong coupling really mean is nothing particularly fancy. It just means that we can actually resolve the photon-dressed states of in this case, a single atom inside the cavity, because what you should view this as, both these levels have a width that scales with gamma. It's a little simplistic here. Of course, gamma should in principle also include relaxations in the material. As long as that width is sufficiently narrow with respect to the Rabi splitting, we can observe these states, which importantly are now, if I think about a wave function for these states, are alpha E0 plus beta G1 are hybrid states of photons and matter. Okay? So, strong coupling, relatively straightforward, right? All that we want is to resolve these hybrid light matter states, even in the case of a leaky cavity. But in general, in this regime, the dipole coupling is going to be much smaller than the frequency of the mode that we excite. Okay? And in particular, this condition allows us to throw away these energetically disfavored counter-rotating terms. The ultrastrong coupling regime is precisely the opposite, right? And is asking about, hey, what happens if G over omega naught, or over omega, goes to 1. And depending on the author of this terminology, this factor here might be some arbitrarily chosen coefficient, but the basic idea is in ultrastrong coupling, you cannot neglect counter-rotating coupling terms, but should really think about the spontaneous generation of photons out of the vacuum from coupling to the material. Okay? And so this immediately tells us two things for these two regimes. So strong coupling generally is achievable at optical frequencies, of course also at lower frequencies, but already at optical frequencies. Why? Well, the coupling to materials might not be so good, but we have access to high finesse optical cavities. So on the flip side, if we're asking about generalizing this to a material, just sort of very conceptually, right, strong coupling requires we put photons into the cavity in order to see these polaritonically dressed states. So in general, we'll need to seed the cavity, we'll need to drive it weakly. So from the perspective of looking at materials and how photons modify materials, these are generally non-equilibrium problems. Okay? The ultrastrong coupling regime is a little different, right? In general, in order to make this feasible, we'll really want to be working in the terahertz regime. Well, lucky for us, many of the elementary collective excitations in materials lie in the terahertz regime. So we'll see this in a second. This is actually a very, very useful regime for us to work in. Technologically, it's a little harder. In particular, cavities are, I'm going to put this in quotation mark, poor in the sense that the optical modes are going to be much less well confined, but we can still achieve large Rabi splittings, as in the dipole coupling to elementary excitations can be made very large. Okay? Interestingly, in ultrastrong coupling, we can now think about, instead of a dynamical problem, an equilibrium problem of the joint state of light and spontaneously generated photons in the cavity. So in particular, right, conceptually, we can think that already photon fluctuations in a dark cavity can change or do interesting things to matter. Okay? Please shout out if there's any questions. I think this is supposed to be interactive like our usual program talks. Yeah. All right, good. So just to give you an idea, right, in optical cavities, G is usually tiny, right, but the finesse can be made very high. In terahertz cavities, factors of G over omega up to and in excess of 1. So I think the largest I'm aware is around 1.25. Yeah?
Sorry, what does a dark cavity mean?
Dark cavity means that we're not seeding it with photons. We're not driving it right? We could say, hey, let's irradiate that cavity using external light to put photons in. In dark cavities, in the ultra-strong coupling regime, even vacuum fluctuations in thermal equilibrium can make a change to the material.
Sorry, and when you say tiny, for the strong coupling, you mean megahertz? Or
What's that?
On the left-hand
the
side.
strong coupling, you mean the megahertz regime? Or?
Oh, so these are typically IR or optical frequencies. I'll show this in a second. It really depends on what system you're interested in. Okay? So typical, right, dipole transitions in atoms that the early quantum optical experiments are made are optical transitions. But in principle, there's arbitrary excitations with arbitrary frequency scales if you pick the right system.
So the deep ultra-strong regime is G over omega greater than 1?
Yeah. So it turns out there's a limit, at least in a simplistic model of light-matter interactions as shown here, that if you make G much larger than omega, there is an effective dynamical decoupling at large interaction energy scales such that the system looks, again, decoupled between photon and matter parts in a rotating frame. So how this extends to solids in general, I think is an open question. Okay, so let's now put our two things together, right? Now, what about quantum optics of correlated electrons? Right. I think it's now fair to say, really pose the two main questions that our program is trying to address, or rather, the community is trying to address. First, can strong coupling to photons change materials? So again, a really broadly kept question, right? This might mean, can vacuum fluctuations change a phase of matter? Can driving lead dynamical phase transitions that are accessible inside optical cavities? The reverse question is equally interesting. What can we learn about materials by interrogating strongly coupled photons? Okay? So the flip side of this is, of course, if I have a photon that is highly entangled with the material, there's a great deal of quantum optical measurement techniques that we might ask, what does that teach us about correlations, entanglement, properties of materials? Okay? So to answer the question about frequencies and scales, well, the good news about solids is that they're incredibly flexible. The bad news is that they're also quite complicated. So what are our emitters? Or what is the analogy to a single atom in a solid? Well, in general, I have a wide range of energy scales. If this axis is energy in a typical solid and this is 0, right? So I'm looking at energies of excitations above the ground state. I might start from low energy collective excitations, which might be magnetic excitations, which might be Higgs oscillations in a superconductor. I'm just throwing out buzzwords. Essentially, think of this as the solid spontaneously develops long-range order at low temperatures. There are fluctuations around that order. Modes for this usually lie down here. Okay. There are lattice vibrations. So we'll have what we call phonons in the crystal lattice. Each of these atoms can move a little, they can vibrate. These collective excitations are very important, for instance, for conventional superconductivity.
Why phonons do not start from 0?
Well, because judiciously I've picked optical phonons, which will couple to light. Yes, good point. Yeah. So I'm looking in particular at phonons that look like this, for instance, right? Right, which are dipole active. So now at higher energies, right, we'll have excitons, interband excitations, excitations in which really the behavior of individual electrons matter. We're exciting electron-hole pairs between different orbitals, between different bands in a solid. But to give you an idea about the breadth of scales, these typically lie in the terahertz, and this can be all the way up to infrared or visible frequencies, suggesting a great deal of approaches to leverage cavity designs to change matter. Okay? So what can we do?
Sorry, just a naive question.
Uh-huh.
You are mentioning these energies because you have in mind the resonant condition, but in the ultra-strong coupling, for many effects, you don't really need that.
That's right. If the coupling strength is really, really large, I might not care about a resonance condition, and I'll give an example for this. Okay. So what can we do, or rather, what can we hope to do? Okay. So the simplest scenario we could hope is to dress electronic bands. I'm just giving you a schematic idea of possible routes to leverage cavity modes. I might have an electronic band in a solid or a band structure that looks something like this. Okay, suppose I have two bands. Need a little more space. Okay, I have two bands. Now, these might be the two bands in, say, a semiconductor. But as I couple a photon, typically in IR visible frequencies, I can now dress each electronic state with a photon, where this here is my cavity photon frequency. And again, get a hierarchy of light matter dressed states in which I now talk about the single particle states of an electronic band. So if this is the electronic state at momentum k with 0 photons, this would be k with 1 photon. This would be a valence band state. Let's give it subscript v. This would be a conduction band with a state with 0 photons, and so on and so forth. And in the same way as we've discussed single atomic emitters, we can now ask, hey, if there is a coupling, a dipole coupling between photons and matter, right? These states will hybridize and generally lead to effective dressed single particle band structures that are combined hybrid states of light and matter. Two interesting things happen, right? So on one hand, I might introduce a Rabi splitting in solids in analogy to what we've seen in atoms, right? And that's already very interesting, where you could imagine, let me change the kinetic energy of electrons. This might change the collective properties. In this case, though, we have to be careful, out of equilibrium, right? Because these are excited states, so we need to populate them. At ultra-strong coupling, even without photons, right, this state here might become dressed and potentially renormalized to have a reduced dispersion, typically a reduced dispersion from vacuum fluctuations. Okay? Both of these effects can conspire to give us interesting ways of controlling the kinetics of single electrons, and thereby change the interplay between interactions and kinetics to give us access to new states of matter. Okay? Now, this is a hard problem, right? Either we need very, very good cavities, very strong coupling, or we need to understand something a little more elaborate about the dynamics of electrons and photons, as most of the interesting things that happen up here for excited states which are intrinsically out of equilibrium. Right? So, two.
So this stress photons with small dispersion, can you tell us why they're interesting for the applications? Or?
Yeah, so there's many reasons, right? On one, so here's the most naive reason, right? Suppose you change the kinetic energy. The combined dynamics of many electrons is governed by, the interplay. What do electrons want to remain mobile by maximizing their kinetic energy, or do they want to freeze, for instance, to minimize their Coulomb repulsion? This allows you to use a cavity to change the relative interplay of these scales. There's more interesting things that can happen, though, right? And I don't really have time to discuss this in much detail, but there are certain band topological properties that we can ascribe to the orbital character of electrons as they move in a particular band. And so these kinds of hybridization effects can actually engineer types of topological states with distinct electromagnetic signatures. So I realize that's a couple of buzzwords and not really answering the question, but think about these hybridizations not just as changing energetics, but also changing the orbital character of the electron at any given momentum as it propagates through the solid. All right, so we could aim to dress collective excitations at maybe elementary collective excitations in a solid, maybe bosonic degrees of freedom that provide an ingredient to provide the necessary glue to induce interesting electronic behaviors. A paradigmatic example is a superconductor. So in a nutshell, superconductivity is described via the pairing of electrons. So electrons feel an effective attraction that is mediated via vibrations of the lattice. Okay, vibrations of the lattice will lie down here in our spectrum of excitations in the solid. So we might hope to change, say, the structure and the coupling of phonons by addressing them with light in terahertz cavities, and thereby modify properties of electrons as they interact with these phonons. Right. So the basic picture that I'm going to draw just schematically is you have an electron gas. These are electrons filled up to a Fermi energy in a metal. These electrons are going to interact with lattice vibrational modes, right? In this case, say an optical phonon mode, right? And this optical phonon mode sits at a finite frequency, okay? But if we now couple this mode to a cavity photon, right? So this energy is going to be omega phonon equals omega photon. Sorry, I hope you can discriminate between these words. I should again expect a splitting into two polaritonic states with a modified coupling to the solid. So without doing any computations, at least we could expect that something changes. Does it change for the better? Does it enhance superconductivity, for instance? Hard to tell, and in particular, unfortunately, generally no. But nevertheless, you can induce an effect just via changing the dielectric or the electromagnetic environment. Okay? I want to give one more example that lies in the deep ultra-strong coupling regime. And then conclude by giving you a brief idea of why the problem is so hard and what we're trying to address. Okay? So the third example is to modify ground states in dark cavities. One example would be, suppose I have, again, an energy of excitations that I'm going to draw as energy minus E ground state, right? So I'm going to have my ground state here. I will have some elementary excitations here. These elementary excitations in my light matter coupled system are, again, a collective mode, but also a photon in the cavity. As the photon in the collective mode gets coupled, right, and there might be more excitations here, right, the hybridization at strong coupling, or sorry, at ultra-strong coupling, will lead to a polaritonic dressing that might in general take a very complicated form. Let me draw on the horizontal axis the strength of light-matter coupling. Okay. As I increase the strength of light-matter coupling at some coupling strength in the ultra-strong coupling regime, I might reach the point where one of my collective modes softens so far that the phase of matter that I have becomes unstable. And this might signify a phase transition to something new or a transition to a disordered state. In either case, a way by attuning the coupling of a photon field to matter to stabilize or destabilize a new state of matter. Okay? You could also imagine, somebody pointed this out, even if I'm off resonant, I could think about counter-rotating processes in a deep ultra-strong coupling regime to engineer ground state properties. One example of this might be a magnet. Suppose I have a magnetic material. Pick your favorite frustrated magnet. The circles are ionic sites on each ion. Suppose I have a single magnetic moment that forms at low energy, at low temperatures. Okay, so I might have, say, an antiferromagnetic pattern that looks like this. Yeah. If I look at how the excitation spectrum of such a system looks like, again, our favorite diagram, energy above the ground state, there are going to be some magnetic excitations. Let's pretend they're gapped, so there's no Goldstone mode. There is a charge excitation spectrum at high energies. Okay, these are magnetic excitations. This energy scale is typically on the order of electron volts. This is going to be in the terahertz. And we could design a cavity in which the photon field is now off resonant from charge excitations. But of course, still couples to charge, right? Photons a priori couple to charge, not spin. So what can happen is that virtual absorption and re-emission processes of that photon back to the ground state or to a magnetic excitation, or a Raman scattering process to a magnetic excitation, can lead to an effective renormalization of the coupling between different magnetic moments. Right? All that this is telling you is that coupling, strong coupling or ultra-strong coupling to photons can change energetics. And so you need to trust me that this actually also coincides with changing the particular order of the many-body state that this describes. Okay, good. So there's many more examples. And so part of the challenge for us is to bring order into the breadth of questions. But one commonality, or a few commonalities, are that the theory is hard to solve. So let me give, as sort of a concluding remark, a cartoon of a theory that we all know and love, but don't really know how to study, which is the Hubbard model of correlated electrons. I could write down a Hamiltonian for a simplified model of a solid, where every ion in its valence orbital has room for exactly one electron, yeah, or one electron with spin up and down, right? So I could have an electron here with spin up, an electron here with spin down. I could have an ionic site with an absence of an electron in its valence shell, or a presence of an additional electron, right? These are my possible configurations. And our minimal Hamiltonian that we might write down, which looks extremely simple, but is in fact not, looks like this, okay? So where I can take electrons on sites I and J, which are my lattice sites, and hop them to the crystalline lattice, coupled via a matrix element T, which we usually call a hopping. There's a Coulomb repulsion between electrons on the same side. Let's pretend the Coulomb interaction is screened in the solid right at low energies. The effective Coulomb interaction might be short-ranged, so I might, at least in a cartoon, only care about the local repulsion of two electrons on the same side. And there is a photon mode in the cavity. Okay, and there might be lattice degrees of freedom. Now, I haven't said how the photon couples to electrons, and in fact, in very generality, we don't know, but we can make a guess. We can make a guess based on gauge invariance, which is the pile substitution, where the photon couples via a phase as an electron hops to the lattice from sites I at position Ri to site, from site J to site I as a function of the magnetic vector potential, dr. Okay, and that magnetic vector potential, again, will give us something like G A plus A dagger for our quantized single photon mode. Okay, that's a difficult problem. Yeah, and just to give you an idea of what the big challenges are, right? So first, this is all at strong coupling. Yeah, so there's no obvious perturbative scale in the problems that we're interested in, right? There's, of course, questions how to handle it theoretically. One thing that we might do is, hey, let's just throw away the photons, let's integrate them out, right? If we did that, keep in mind we kept a single photon mode, and the photon wavelength is much larger than the lattice spacing. We get effective long-range interactions between electrons. So that automatically means that many of the tools that we use in condensed matter physics to understand correlated electron problems, in particular many-body computational tools, fail to apply because they intrinsically make an assumption of for locality. So one thing that one might posit is that this will require new many-body computational tools. Also, fundamentally, many of the regimes that I've discussed are intrinsically non-equilibrium problems. So not only do we have to understand a strongly coupled problem, but also we have to understand its dynamics, at least at low photon number, and particularly due to being driven with photons, but also due to dissipation. Since cavities are intrinsically leaky, we put photons in, they're not going to stay there for an infinite amount of time. So the problem that we really like to solve is a strongly coupled, driven, dissipative problem of a solid. But on the flip side, there's plenty of exciting prospects on the horizon, right? Ranging from trying to zoom in on simple mechanisms of dressing elementary excitations to finding fundamentally new and dynamical states of matter that are arise in a driven, dissipative, out of equilibrium setting. All right, and I think now I'm pretty much out of time, so maybe let's open up for questions.
So is some model plus A? So is the model in one dimension better understood, or in one dimension also not?
Did you say one dimension?
One dimension, I and J.
Oh, there's no reason to make this in one dimension, right? So you could interpret these as generic lattice coordinates.
But I and J, I can arrange. So can I have equal lattice with one dimension for the operator?
Yeah, absolutely. I mean, you could imagine taking something like strontium copper oxide, which is well captures essentially decoupled one-dimensional chains. Then if you were able to exfoliate this down into a really thin film and put it in a cavity, the physics that you should study is an effectively one-dimensional Hubbard model.
Yeah, with the model in one dimension is better understood analytically.
Yeah, so unfortunately, with coupling to light, the ground state of the Hubbard model in one dimension, of course, is exactly solvable via beta ansatz. The light matter coupled problem is not, right? And so you can intuit this from, again, integrate out the photons. You're going to generate long-range interactions that are outside solvability.
Yes. Yeah, maybe it's more of a comment than a question. So you mentioned before that we have this, quantum optics nomenclature of weak, strong, ultra strong, deep strong, what have you, comparing G over gamma, G over omega, and so on. But now we have a continuum of excitation, right? So even the whole nomenclature of quantum optics is has to be reinvented.
Yeah. So so the G that we posited in a single atom, right, considers a single dipolar transition. I think there's a relatively straightforward way of generalizing this to an isolated collective mode that we want to couple to. But as soon as we talk about, say, the band structure engineering here, that Rabi splitting here, does not have a simple single dipole transition interpretation in general, right? And the same is true for the cavity, quantum magnet, etc. For each of which we need to really ask what is the effective coupling, or what is the effective perturbation of the ground state as a function of all the possible processes by which photons can scatter off matter.
So I think I would add this to the list.
Okay.
One question.
Yes. So all of this sounds very complicated. Can you calculate something that we know, such as refraction index?
Again, in limiting examples, we can. Yeah. So
just a crystal of silicon, and we just put all the properties, and you can give us refraction index.
yeah. So suppose you give me silicon. I can give you the refraction index, but I would also argue that limit is precisely not the limit that is particularly interesting, right? So that's a limit in which we can perturbatively understand the coupling of light to solids, which is precisely not the limit in which you change the material itself. So in a sense, right, the question is posed in such a way to circumvent the simple solvable examples.
So a few questions on the numerical side. I assume you have a science problem. Is there some variant ratio of the couplings, maybe UNT, where we can solve it in Monte Carlo?
Yeah. Actually, that's something. I'm interested in, and actually doing a little bit of work myself. I didn't qualify this very much. Maybe I should say, just highlight three things. Right? Our favorite tools of choice are usually, at least at exact tools, tensor network approaches, or DMRG, quantum Monte Carlo, or DMFT for the complexity of solids. All of these have an assumption about locality, although for quantum Monte Carlo, that assumption can be relaxed. And indeed, there are one thing that we can hope to do as a community is to understand limits of such a complicated model, which are computationally solvable without a sign problem, which do exist.
Yeah, I guess when I saw the eye of the exponential, one of the first questions that came to my mind is this really Hermitian? Like, is the Hamiltonian really a Hermitian matrix? Because, like, how is that?
Yeah, so an electron hop, suppose this is J and I, right? An electron hops from J to I, picking up a phase, right? If the electron were to hop from I to J, right, the limits on that integral would change, so the phase would be negative.
Oh, okay. And then I guess the question then also, like, follow-up is how do you incorporate, let's say, phonon interactions, or just like interactions that we just
Yes. So it's hard enough, but we've missed a lot of complexity. We haven't talked about vibrational degrees of freedom. In fact, we've even just singled out a single orbital in the solid, right? So all of these can be incorporated, and our best bet is to build an effective theory by choice and by selection of energy schools. Yeah.
I mean, you mentioned what can we do with that, but and there is a lot of stuff, but like, what is experimentally solid in your opinion? I mean, how all of these relate to the experiment?
Yeah, so I think that's a great question, right? So on the quantum optics side, single or few emitter systems are now extremely controllable, right? So we can use them commonplace as platforms to simulate simple quantum mechanical systems. Of course, on the quantum optical side, the main issue is scalability, right? So hundreds of atoms is doable, 10,000s of atoms is hard, or is impossible. In solids, we don't have that problem. We have a fundamentally many electron problem. So quantum optical techniques immediately scale to systems where we can consider, say, a thermodynamic limit. Now, to your question, what's been done experimentally, it's first examples of changes of material properties by light have been found. So I'm ignoring all of the tremendous efforts in the ultra-fast community of shining strong classical fields, but really just focus on cavities. There's examples of manipulating so-called quantum Hall states with cavities. There's examples of changing properties of superconductors or magnetic films with cavities. What's been shown and now is increasingly well controlled, and that's really a technological challenge, is how do you design cavities, particularly in the terahertz, that are good enough to even achieve strong coupling to collective modes. And we now have numerous examples in which couplings deep in the ultra-strong coupling regime are achieved for, say, phonon polaritons or other collective excitations in the terahertz. So the challenge here is really the cavity design, trying to think about how to cleverly confine mode volumes using metamaterials, etc.
Can I follow up comment to what Martin said? Is that the difference between this usual quantum optics that is applied to cold atom is that over there you exactly know your Hamiltonian, your two-level system, etc. It's beautiful. You start from bottom up. You know your atom. All atoms are identical. Everything you can do bottom up. Here it's quite a humbling experience for a quantum optics person when it comes to material, because you have some idea, you do an experiment, and there are 5 different theories that can explain the same experiment. So the experiment that Martin mentioned is that they're inspired by these quantum optical ideas, like cavity design, etc. But then you have like 2, 3 competing theories that can explain the same phenomena, which is very natural in a condensed matter setting. Majorana was a good example of it. I'm sure a lot of people have heard. So this has a generic idea that we are kind of working with experiment and theory together to find relevant phenomenological theory.
That's right. So I'd like to say that, as theorists generally, we have there's a really well-oiled machinery in principle to go all the way from a bare scale to an effective theory in equilibrium in ordinary solids. And even that machinery usually breaks down at some step, and then only with comparison to experiment can be refined to single out the effective degrees of freedom, right? And, prominent examples are high-temperature superconductors, which are still under debate. So in out of equilibrium, that machinery doesn't exist in the first place, right? So a lot of what we guess are the right ingredients in theory have to come in hand with experiments to guide us, what is the correct things to look at. If that makes sense as a spiritual answer.
Okay. Thank you very much. I think it's